Have you ever wondered how calculators actually evaluate expressions behind the scene? What really happens when you type an expression into a calculator and hit enter? How does it actually understand something like this? In this series, I'll break it down and show you how data structure and algorithm power these real-life or real-world features behind the scene. Take a look at the demo video. In this demo, we type an arithmetic expression into the calculator like this, for example, and we press enter or the solve button. We click on the solve button. Once we do that, instantly we have the result. But most importantly, right below, we also see the corresponding expression tree showing exactly how the expression is structured and evaluated step by step. In this video, we will first explore a naive way to implement this functionality, then introduce an algorithm that allows us to handle it more efficiently and elegantly. If you are new to the channel, don't forget to subscribe, like, share and comment to support the content. Code with Eno. Before we implement anything, let's understand the project structure and what is required. Our eval tree app is a KivyMD app that you can find in the DSA in real life repo under binary trees/expression calculator. In this folder, you will find three subfolders. We have the starter. This is where you can attempt your own solution. We have the naive. This is where you will see my implementation of the solution using the naive method. And we have the DSA. This is where you will see my implementation of the solution using a suitable algorithm. Let's start the app from the starter folder, okay, and see what we need to implement. So right here we have my terminal and cd into starter. From there, I can do UV sync in case you get this project from the repository. You need to install all requirements. Okay, so since I'm using UV, you can just say UV sync and it's going to install everything from the PyProject file. So once you have that, you can use make. Okay, if you have make set up, then you can just type make and it's going to run the command in this make file, or you can just copy the command here and run it directly. Okay, so once I do that, and I will see my user interface popping up. This is our simple expression calculator called eval tree. The goal is to make sure that whenever we enter a valid arithmetic expression, for example, something like this, the correct result should be displayed here. So once either we press enter or we click on the solve button here, the correct result should be displayed here. And optionally, you can have some sort of visualization to show the step-by-step process used to evaluate that expression down here. Now let's explore the project structure. Like I said before, this is a simple KivyMD project, and here we have the Python file that is the entry point to our project, and it runs also a Kivy language file here. Okay, so this Kivy language file defines the UI that we have here, and the Python file kind of like run the logic behind this UI. Okay, so here we define the theme style and so on. Okay, not really important. What is really important is here we have this soft expression and we have this clear input. So the clear input react to this button here, clear. Okay, and the solve, or when we press enter in here, reacts to this function here, solve expression. So we can see the solve expression calls the evaluate expression and pass in the expression as a string. So if we go to this evaluate expression, it is found somewhere in the DSA. So we can see in the DSA we have a file called evaluator.py, excuse me. So if you go to the evaluator.py, we can see we have here a function expression, evaluate expression, pass, it takes in an argument expression as a string. So here we have some instructions. Here it says your task is to implement an algorithm of your choice to compute the value of the given expression. You may use any data structure, each is stack, queue, tree, and approach, passing, recursion, or built-in methods where appropriate. So this is the requirement. So you have to make sure you support these basic arithmetic operators. You handle operator precedence correctly. You handle parentheses. You also handle decimal numbers. Okay. You accept expression with or without spaces. So we can have different formats like this. Okay. It should be accepted like this or like this. And assume the input is a valid expression. So here we just need to make sure that we pass in a valid arithmetic expression. Okay, so there's no validation for now. Okay, we'll come back to the validation later. And once we have that, we can return the results to be displayed on the UI. So we need to make sure we understand that Kivy, okay, for you to be able to display anything on Kivy, it needs to be a string. Okay, whatever you display on Kivy needs to be a string. So either you return a string here, or you return the integer or floating point number, then you convert it to a string before you display it on this UI. So our implementation will focus more on this specific function. For the naive implementation, we need a simple way to solve this problem. And long time ago, I used to use a Python built-in function called eval to kind of like run some simple arithmetic expression. So let's try it out and see if it will work. So if I say eval and I run this, we can see it is 13. So let's try again, but this time with parentheses to define our precedence. So if we run this, we can see though they're the same, but because here we use parentheses to define the precedence, this will execute first, whereas here this will execute first. Okay, so we can see everything works as expected. So if we try to vary the format like this, put everything together, okay, it still works. And with with decimal points, it will work as well. Okay, so I think for our naive implementation, we can just use this. Okay, it kind of like meets most of these requirements. Okay, so let's make sure we are in the naive. Okay, so yeah, I'm in the starter, so I'm gonna leave this folder, enter in the naive, and in this naive, I'll go to my DSA and evaluator. We can see we have here eval. So all what we do is that once we receive the expression here as a string, we just pass it to the eval and we return it. Okay, so once we have that, let's go ahead and run our application. So here I make sure I navigate to the naive on my terminal and I press make, or just get the command from the make file. So once we have this runs on the naive implementation. Okay, so let's go ahead and say 4 plus 2 times 1. Okay, and we can see we have the result. Let's go again, maybe something like this and something like this. Okay, we have the result. So everything works as expected. Why do we need a powerful data structure? Why do we need to waste our time with a data structure and algorithm? So let's take a look at some limitation that the eval or the naive implementation puts to the table. Some of the limitation that this naive implementation has is that the first one is that it can execute any Python code. So for example, if we do something like this, we import OS, then we try to get the current working directory and it's going to execute. Okay, so this is very dangerous because input comes from the user, so the user can run malicious command or malicious codes into your application. So that's the first thing. The second thing is that eval can run garbage expression. So something like this, if we do eval and we say 5 plus 2, okay, it's gonna run. So this is not an expression that you should expect from a user. So the second thing is that there's no control over the passing logic. You don't get to decide how the expression is evaluated, which means you can visualize computation or debug step by step, or even teach someone how it solved the problem. For example, you can see here in this case we lack the visualization because there's no way to do that. Okay, and the third one is that you get stuck with Python rules. You can really customize the behavior of the eval. For example, to reject invalid expression, to introduce your own operators. You have to stick to the Python's operators. You can actually enforce math strict rules. Okay, so these are some of the limitations that you have with this naive implementation. Let's talk about an expression tree. An expression tree is a special kind of binary tree that can be used to represent arithmetic expression. So let's begin by understanding some definition around expression tree. So we have the first one will be tree. We can think of tree as a hierarchical form of data structure, as there is a parent to child relationship between the items. Okay, and the second one will be binary tree. Okay, so a binary tree will be a collection of nodes. So we see here we have nodes, which will be the next definition. It is a collection of nodes where nodes in the tree can have a maximum of 2 child nodes. For example, we have something like this. All right, so we can see here these letters represent nodes, and these edges or these lines, okay, links the nodes to the other nodes. So this node A has 2 child nodes. Node C has 2 child nodes, that is D and E. Now let's come back to the definition of a node. So a node is a data structure that holds data and references to other nodes, that is the left and the right nodes. Okay, so we can see here this is a node, and the data here, for example, is A, and it has reference to 2 nodes, that is the node that contain B and the node that contain C. So if we want to represent it in this structure, I can use this structure to represent it. So here the value here will be A, and we will have L will represent the reference to the left node, and R will represent reference to the right node. Okay, so let's see how this can be implemented in Python. Alright, so when we move to our DSA folder that contains our solution using the expression tree, the first thing we want to do is to define our nodes, because we know that the nodes is a building blocks for all trees, and we are talking about an expression tree in this case. Okay, so our node is a simple class that has the init method that takes in a data. Okay, and that data is set up here, and here we have 2 object attributes. Okay, so the first one is the left child and the second one is the right child. So these attributes hold reference to the left child nodes and the right child nodes respectively. So here we can see it can be either a node or it can be none. Alright, so back to our expression tree. We said earlier that an expression tree is a special kind of binary tree that can be used to represent arithmetic expression. So what is an arithmetic expression? Okay, what is an arithmetic expression? So an arithmetic expression is represented by the combination of operators and operand, where the operators can be unary or binary. So an example of operators in this case, from our basic math knowledge, we know of plus, minus, division, and multiplication. Okay, an example of operand can be numbers like 2, 4.3, and so on. Okay, so an arithmetic expression can be shown using 3 notations. So we have here notation, okay, and we have the infix, we have the postfix, and we have the prefix. What is important for us to successfully implement our solution is the infix and the postfix. Okay, so this and this. So let's start by understanding what an infix is all about. So this is the most common representation of arithmetic expressions understood by humans, where the operator is located between two operands. So I'm sure that in your basic arithmetic knowledge, you have seen something like this. So for example, we have 4 plus, let's say 1.2. And another example is, let's say 4 plus 5 times 5 minus 3. So in both cases, we can see that we have an operator that stands between two operands. In this case, plus stands between 4 and 1.2. And here we have plus standing between 4 and 5, and multiplication standing between 5 and 5, and minus sign standing between 5 and 3. Now, we have talked of binary tree, okay, and we have talked of expression tree. And we said an expression tree is a kind of binary tree. So now, how do we represent, for example, something like this as an expression tree? Okay, so there's a simple rule we need to follow in order to represent this as an expression tree. The rule is that all leaf nodes should contain the operand, while the non-leaf nodes should contain the operator. So when we talk about the leaf nodes, we're talking about those nodes that have no child nodes. Okay, so when we talk about, let's take a look at this example. So here, this is a leaf node, this is a leaf node, and this is a leaf node, and this one is a non-leaf node. So when we talk about the leaf nodes, leaf, or let's say let me use this instead. Let me say leaf nodes. We are talking about here B is a leaf node, D is a leaf node, and E is a leaf node. So for the non-leaf nodes, we'll talk about A, we'll talk about C. Okay, now coming back to this example, if we want to represent this, let's follow these rules. Okay, so if we follow the rule, we'll see that we have 4, which will be a leaf node. 5 will be a leaf node. 5 will be a leaf node, and 3 will be a leaf node. Okay, so what sits between 4 and 5 is a plus operator. So we have here plus. What sits between 5 and 3? We have the minus. Okay, minus. We have the minus that sits between 5 and 3. So we can see here, and now if we extend this to the roots, we have the multiplication. Okay, so I know this is difficult to understand this way, but we'll take a look at different ways by which we can represent this. Okay, now if we are given this kind of expression tree, and we are asked to come up with the expression, okay, the infix expression from this expression tree, then a few things we need to follow is that in order to generate an infix expression from an expression tree, is that we need to first visit the left nodes recursively. Once we visit the left node recursively, we go ahead and visit the root nodes. Once we visit the root nodes, we go ahead and visit the right nodes recursively. So this is called in order traversal method. Okay, so this is an in order traversal method. So if we use this in order traversal method in order to get the infix expression from this expression tree, we will see that we need to first visit the left nodes So left node recursively. So we come here, left node, but this node is a root node of a subtree. So we go again down to the left node. So we have 4. So we see that 4 comes first. And once we have the left node, we go ahead and visit the root node. So the root node of this subtree is plus. So go ahead and say plus. Once we have visited the root node, we go ahead and visit the right node. So the right node is 5. Alright, so here we see that in the bigger picture, we have visited the left node. Okay, so we did all those things in the left node. Following these rules, it says visit the left node, then visit the root node. So we are done with the left node. Okay, so we come back to the root node here, which is multiplication. Once we are done with the root node, we go now to the right node. And in the right node, we do the same thing. So once we are in the right node, we follow the same rule here. We visit first the left node, which will be this one, which is 5. We visit the root node, which is minus. And finally, we will visit the right node, which is 3. Okay, so we see that we have our infix expression. And we can see that this is what is used in most arithmetic expression. Okay, so we have operand, or we have the operator between operands. Okay, so we have the infix, okay, and the infix tells us or gives us an idea of how users will enter their arithmetic expression into our calculator. But the infix expression cannot be used directly in order to get the results. Okay, this is because of issues with precedence. So the infix expression cannot represent precedence correctly. So let's take a look at an example. So we have this. Let's say this is the first example, and the second example will be this. Here we want to manually control the precedence. Okay. So we see that here, of course, the multiplication sign has a higher precedence over the plus and minus. Okay, so execution here will take place like this. So here we will have first 5 times 5. So we'll have 4 plus 25 minus 3. Okay, that's how it will be executed. So here the expression in the parentheses will be executed first. So here we will have 9 times 2. Okay, so we can see here at the end of the day they have 2 different results. Now the thing is that both example 1 and example 2 can be represented with the same expression tree here. Okay, so we see where the problem is coming from. So if you give this, it will be represented as this expression tree. If we give this, it will be represented as this expression tree. So we can see here that at the end of the day, if we generate back the infix expression from this expression tree, we will have something like this. We'll have 4 plus 5 times 5 minus 3. And we see here that we lose all control of the precedence. So this is an issue that this is the issue that we have with the infix expression. In order to resolve this, we need to transform the infix expression into the postfix expression, because the postfix expression actually represents the order of execution or represent precedence correctly. In order to transform our infix to postfix, we can use the shunting yard algorithm that has these following rules. Here we are going to use 2 containers. The first one will be the output that will contain the operand and the final expression. We are going to use also a stack that is going to temporarily hold the operators and parentheses. Here we need to respect the precedence of the operators and we need to handle parentheses. So let's take a look at an example. So we have here example. We are going to use this, okay, times 2. Alright, so we are going to loop through this expression, and for each item in this expression we are going to follow these rules. Okay, so let's say for example, and also please, we are going to represent the output as O and stack as S. Okay, so that is easy for us to understand. So let's say the first loop is going to consider the open parenthesis. So what does it say here? The open parenthesis or parentheses are temporarily held in the stack. So for this, we know that the stack is going to hold the open parenthesis while the O remains empty. So the next loop is going to consider 3. What does it say? The output holds the operand. So here the stack stays with the open parenthesis while the output holds 3. The next one will be plus. So the plus here is an operator. And what does it say here? The operator are temporarily held in the stack. But before we go ahead and push this in the stack, we need to check some conditions. So whenever we see an operator, we need to loop through the stack, okay? Loop through the stack. If we find an item that has a precedence greater or equals to this operator, then we go ahead and pop it out of the stack and add it to our outputs, okay? And as we are looping through the stack, the item should not be an open parenthesis. So we can see here that there's nothing to loop here, okay? The stack contains the open parenthesis, okay? So as we are looping, we should make sure that we consider only operators, okay, that have precedence greater or equal to the operator we are considering, and it should not be an open parenthesis. So here, since we have the only item that is in this stack is an open parenthesis, we just go ahead and follow the rules. We add the operator to the stack. So here we have the stack will have open parenthesis and plus, while O will maintain its 3. So the next loop we have 5. We'll go ahead and just follow the rules. The stack contains the open parenthesis plus, and the operator has 3 and 5. Okay, so the next loop we will consider the close parenthesis. So the rule is that once we have a close parenthesis, we'll go ahead and loop through the stack, okay? And as long as we don't hit an open parenthesis, we go ahead and pop everything, okay? Pop everything, pop the items that we find. As long as we don't hit the open parenthesis, we pop it and add it to the output. So if we consider the stack at this moment, we see that the stack has the plus operator and the open parenthesis. So what do? We check, we look through the stack, we get the plus here, which is an operator. We go ahead and pop it out and add it to our output. So we have here 3, 5, and plus, okay? So once we do that, we go ahead and remove the open parenthesis from the stack. So the stack will stay empty. So the next one is the multiplication. So loop 6, multiplication. So in this case, we just follow the rules. We add it to our stack. So our stack will have the multiplication, while our output maintain 3, 5, plus. So the next one, which is the last one, will be 2. And here it is an operand. So we go ahead and just push it to our operator. We just go ahead and push it to our output. So here S, which is the stack, will maintain our multiplication, and the output will have 3, 5, plus, and 2. Now at the end of our loop, we go ahead and remove everything from our stack into our output. So the stack will remain empty, while the output, which holds the final expression, will be 3, 5, plus 2, and multiplication. So we see that this is the final representation of our postfix expression that we got from this infix expression. Now, to see how the same infix can be represented differently when transformed to a postfix, let's consider this example. So we understood that these two are represented the same in infix expression, right? Okay, so let's consider this here. So we loop through this to see how this will be transformed to a postfix. So we start with the first loop, which is 3. 3 is pushed to the output because the output holds the operand. The next one is plus. We see that when we have an operator, we need to loop through the S to check some condition, but here there's nothing to loop here. So we go ahead and add it to the stack temporarily. And the next one will be 5. 5 will go ahead and add it to the output. And the next one is multiplication. So multiplication, we go ahead and look through the stack. And what we're looking for? We are looking for operands that have a precedence greater or equals to this operand. And that is not also an open parenthesis. So we can see here that the only operator that's in the stack has a precedence lesser than the multiplication. So we see here that the rule fails. So because the rule fails, we'll go ahead and push the multiplication to the stack. So the stack contains now our addition and multiplication. So the next loop is 2. We go ahead and add it to our output. And at the end, because we are at the end here, at the end we go ahead and remove everything from the stack into our output. So when we do that, this is what we have. We have 3, 5, 2, multiplication and addition. So we see that at the end, it is not the same as this one, right? They have two different representations coming from the same infix. What changes? The change here is based on the precedence of the operators. Here we are using the parentheses to control the precedence, whereas here the precedence is controlled by the operators themselves. Okay, so we can see here that the reason why we actually transform an infix to a postfix is because the postfix actually represents the order of operation correctly. Alright, so to see how this is implemented in Python, we have this function, the infix to postfix function, that takes in an expression as a string, and here we define the operator precedence. We can see here that multiplication and division have higher precedence over addition and subtraction. So here we have our stack that holds our operators, and we have the output that holds the operand and the final expression in postfix form. So here we split, okay? We split the expression that comes here as a string. So for example, if we receive this, then it is split to this. And we look through this list, and for each token, so we represent each of these as token. For each token, this check if we have an operand. So let's say an operand, in this case, is a number, okay? So if it's an operand, we go ahead and push it in the output. But if it is an open parenthesis, we go ahead and push it in the stack. If it is a closed parenthesis, we loop through the stack. As we are looping through the stack, as long as the item we receive from the stack is not equals to an open parenthesis, we go ahead and pop it out of the stack and add it to the output. And at the end, we go ahead and pop the open parenthesis. So this line will pop out the open parenthesis. If we encounter an operator, then we loop through the stack again. As long as the item we are getting from the stack as we loop is not equal to an open parenthesis, and the precedence of that item is greater or equal to the precedence of the token, then we go ahead and pop that item from the stack and add it to the output. And at the end of the day, we go ahead and pop out that we go ahead and add the token or the operator into the stack. So once we have done, once we have looped through all the items here, we go ahead and remove everything from the stack and add it to the output. So this is the same thing I demonstrated earlier. Okay, so this is how it is implemented in Python. Once we have transformed the infix to postfix, the next thing we want to do is to generate an expression tree from the postfix. And to do that, we can use this simple algorithm where we look through the expression or the postfix expression, and for each item in the postfix expression, we go ahead and create a note of that item. We check if the note is an operator. If it's an operator, we pop two notes from the stack, okay, because it uses a stack to hold these notes. We pop out two items from the stack. The first one will represent the right child, while the next one will represent the left child. Once we have these two notes, we go ahead and make them children of the newly created node. Once we have done that, we go ahead and push the newly created node back to the stack. Okay, we do that for each item in the postfix expression. Let's take a look at an example here. So we have 3, 5, 2, multiplication and addition. So if we loop, the first loop will consider 3. We go ahead and push it to the stack because, of course, it's not an operator. So we just go ahead and push it in the stack. Okay, we create the node. Once we create the node, we push it in the stack here. So do the same thing for 5. We do the same thing for 2. Okay, so the next item will be the multiplication, which is an operator. So once we create the node, we check it is an operator. We go ahead and pop two nodes from the stack. So let's pop the two nodes. So the first one will be 2, which will represent the right child, and the next one will be 5, which will represent the left child. Okay, so once we have that, it says we have to make them children of the newly created node. The newly created node is x. Okay, so we have here x, and once we link the children, 2 will go to the right and 5 will go to the left. So once we have that, we go ahead and push the newly created node to the stack. Okay, so when we push that to the stack, our stack now becomes this. So we have two items here. The first one will be 3, and the next one will be the node x that have these children. So I'm going to represent it, break it down into a postfix expression, okay, because this is an expression tree. Okay, break it down to a postfix expression. We have left, which is 5, right, which is 2, and the head or the root, which is multiplication. Okay, so this is a way of traversing a binary tree or an expression tree in order to generate a postfix expression. So what do? We first visit the left nodes, then we visit the right nodes, then we visit the root node. So that's exactly what I did here. All right, so let's move to the next loop. We have plus. So we have the first one will be this one, okay, which will be 5 to x. And the next one will be 3. So this one will represent the right nodes, and this one will represent the left nodes. So once we have this, we go ahead and make them children of the newly created nodes. Okay, so it means here the newly created node is plus, so plus is here, and on your right we have this sub tree or this sub expression tree. So here we have the head, which is x, and the left node of that head is 5, and the right child of that node is 2. So once we are done with this right, we go to the left. The left now has 3. Okay, so this is the expression tree, okay, of this postfix expression. Let's see how this is implemented in Python. So here we have a function called createExpressionTree that takes in an expression as a list of string. Okay, so here we define our stack, which is empty, and we look through the expression. We create the node with the item, and we check if the item is an operator. If it's an operator, we go ahead and pop two items. So the first one will be the right child, of the newly created node, while the next one will be the left child of the newly created nodes. So once we do that, we go ahead and push the newly created node into the stack. Okay, so once we have done all of this, we go ahead and pop out the first node into this we go ahead and pop out the first node of the stack. So here, definitely what we're doing is that we are getting the roots. Okay, we're getting the root of the expression tree, because that's all we need. Okay, because the root has references to all the other nodes of our tree. Once we have created our expression tree here, we go ahead and use this function that receives the root nodes and call itself recursively by checking the different operators that we support. So here we do the calculation and return the results. And here we have the evaluate expression, that is our main function that is called from the main.py. Here it receives the result and pin it to our UI. So here, what does it do? It receives the expression, transform it to a postfix, create an expression tree, and does the calculation. So before we run our application, let's go ahead and check a few things. There's something that I left out here. So at this level, where we create our expression tree, here we create the nodes. The nodes will be, the data in the nodes will be a string, okay? Being in an operator or an operand, all of them will be a string. So if we come here to this calculation here, this will not behave the way we expect, because the addition here will instead concatenate the string instead of adding them, okay? And here this one may fail and so on. So we need to make sure if we have an operator, we can leave it as a string, but if we have an operand, then we can convert it to an integer or a float. So here, what do? I can remove this and put it in here. And here I have an else statement. In case it is an operand, then I go ahead and convert it to a float. Okay, so once I have that, then I can go ahead and run my application and test it. So 4 plus 3, I have 7. 4 plus 3 times 2, or times 2, I have 10. Because here the multiplication will work first. So 3 times 2 is 6, plus 4 is 10. If I go ahead and put parentheses here, okay, it fails. Let me put a space here. Okay, so here I have 14. So we already see the limitation that we have with this. Okay, so we are going to see how to fix that. So far we're able to evaluate our infix expression and see the result, even though we lack the visualization here and a few things that we're going to see very soon. Let's check some limitations and see how we can resolve them. So what works is that if we pass in 4 plus 3 like this, everything works as expected. But if we remove a space here and we try to solve this, we see this is not the desired result. And if we remove completely all the spaces and try to run it, we have invalid expression. So what happened is that during the split, we split take into consideration that we have spaces like this. But now when the spaces are not there, we have issues. So the second thing is that we cannot actually process decimal numbers. So if we try to process a decimal number like this, it's going to fail. So how do we fix this problem? If we go back to the top of our code, we can see here that instead of splitting like we did before, we use the simplify expression in this case. So let's check what it does. So the simplify expression actually handles two things. It handles the decimal numbers and the spaces. So here we look through the expression and we check if it is a number or it is a point. So here we try to join the decimal numbers together. Okay, so let's say we had 4.3 or 4.2, sorry. So what it does is that it checks if I is 4, it adds it to the result. If it's 6 point, it adds it to the result. And if it's 2, it adds it to the results. Okay, so that we have our decimal number at the end. Okay, but if it is not a numeric number or a point, we go ahead and add the appropriate space. Okay, so that's what it does. So at the end of the day, we handle the decimal numbers and the space. And here we have the is number, and the is number here, just make sure that we can handle floats, because if we remember the if we have something like this and we say it's numeric, it's going to say false. So there's no way we can check if this is a floating point or a decimal number. Okay, so to do that, we use this method. And how do we use it? So we go ahead and use it yeah. Okay, so once we split everything using the simplify expression, we go ahead and look through the token and check if it is a decimal number. Okay, so that's what we do here. And once we do that, and here we already handled this in our previous section. So once we have this, we can save it and go ahead and run it again. So once we run it, I can go ahead and say 4 plus 2, and it gives me the right results. So I can remove the space here and maintain, I can add the space here and maintain the empty space here, and it gives me the same result. Okay, and I can use decimal point. Okay, and it gives me the right results. All right, so to round up this section, we are going to add the visualization. Okay, so how do we do that? We have this code here that handles the visualization. I'm not going to go through the code, but you can check it and see what I did here. Okay, so once I have this set up, I go ahead and import it in my main.py. Then in my Kivy language file, I just go ahead and define it here. Okay, giving it an ID. Okay, and back to my main.py, I have two functions here. The first one is to display the tree, and the second one is to clear it. So in order to display the tree, we can see here the display the tree takes in the root. Okay, the root of my tree. So I need to return the root of the tree as well as the result from this evaluate expression. So that's what I did here. If you come down here, you can see here I returns a tuple. Okay, I return a tuple, the result of the calculation, and the root of my nodes. So once I have that, I can come back here and do something like this. 5 plus 3 times 2, press enter, and I can see I have my result plus the expression tree that is generated. That's it for this video. We just saw how we can use an expression tree to evaluate an arithmetic expression by building our expression calculator called eval tree. Thank you for watching. Be sure to come back for more as we keep exploring data structure and algorithm and how they apply in real-world scenarios. Of course, you are encouraged to review the starter codes and build your own implementation. If you believe there's a data structure or algorithm that works better than the expression tree we just explored, I would love to see your version. Go ahead and fork the repo, implement your solution, and submit a pull request. If you're new to the channel, don't forget to subscribe, like, share, and comment to support the content. Code with Eno. See you in the next video.